In this work, we introduce a robot design and motion co-optimization method based on physically consistent mesh model. My name is Jaewoon Kwon, researcher working with Naval Labs in Korea, and this is a joint research with Seoul National University. As you can see on the left, a few kinds of general-purpose robots are doing various different tasks in automated factories. Sometimes, even a large robot has to carry a small thing in a short distance. This is because it has been impractical to have task-specialized robots or robots that are optimally designed for each task due to expensive cost of both fabrication and design. While the fabrication is becoming a lot cheaper by recent advances of rapid prototyping technologies such as smart connectors, 3D printers, and others. Automating the complex design process is still an active area of research. Thus, our goal is to solve this motion design co-optimization or co-design problem that simultaneously optimizes the robot design and motion for a given task. This problem is evolved from a traditional problem of motion optimization. It finds an optimal motion of a fixed design by minimizing a motion cost while satisfying a set of task constraints, such as matching desired end effector poses and joint limits. Adding a design parameter such as link lengths to here as a variable denoted by rho, it becomes the co-design problem that has an additional constraint, so-called design model. The design model is a parameterization of the robot kinodynamic model parameters, such as joint axis and link masses. However, while this has been often approximated by primitive shapes like boxes and cylinders in previous methods, we've verified that even a small approximation error can induce a large performance drop. To address this issue, we propose a method that accurately parameterizes the link shapes by triangular meshes and use it to compute the inertia parameters exactly. We then solve the optimization problem using analytic gradients. As is well known, the analytic gradient is much better than the numerical gradient in both computational speed and accuracy. To obtain the gradients, we derive a recursive algorithm for the differential dynamics with respect to the kinematic parameters. In this first experiment, we consider this 6DOF manipulator conducting a simple pick-and-place task to verify the effectiveness of our co-design method compared to the traditional motion optimization. As seen in the above, the motion-only optimization with a fixed design cannot successfully achieve the task if the picking and placing distance is too close or too far because of the joint limits and the limited workspace. However, the co-design method at the bottom achieves the task by adjusting the link lengths properly and reduces the motion cost at least 50% for all distances. This second experiment proves the importance of using accurate link geometries rather than simple primitive shapes. The previous pick-and-place task is now under a dynamic constraint, such as a bounded ZMP. Because of the approximation error of the link inertia parameters, the ZMP of the primitives also has small errors compared to that of the meshes. What we want to emphasize here is that while the ZMP error is small, the adjustment of motion to satisfy the constraint could be very large, which cause a large drop of performance as well. The third experiment is to prove that our method can be also applicable to parallel mechanisms. Compared to the left initial design of equal lengths, the optimal design on the right has longer links for those directly connected to the motors to minimize the motor movements and the energy loss. Lastly, we verify that our method works well not only for simulation, but also for the real robots. For a pick-and-place task with a certain distance, the energy efficiency is improved about 60% in simulation. And surprisingly, This number is almost realized with the actual hardware shown on the left. To summarize, this work addresses the co-optimization problem of robot motion and design for a given task. A key to success is to achieve sim to real, which means that the improvements predicted by the numerical optimization must be exactly realized by the real robots. To achieve this, we parameterize the link meshes and use it to obtain the accurate kinodynamic model parameters. For the gradient-based optimization, we also propose a recursive algorithm for the differential dynamics with respect to both motion and design parameters. Thank you for listening.